So what we now want to do is to develop a computationally light metric that won't take that much time, but it will capture that what between a centrality captures. So what does between a centrality represent? It represents what? The fraction of the shortest path between any two vertices going through a specific vertex. So let us say if this is a given graph, this is a between a centrality of all the vertices. We want to say rank the vertices based on between a centrality. So based on the values here, which vertex has the largest between a centrality? Vertex 5. Okay. Then you have vertex 4, then vertex 2, and then vertex 1, and so on. Again, 0, 6, and 7 have between a centrality of 0. So if you want to get a ranking of the vertices based on between a centrality, what I am going to show is it's not necessary to really compute the between a centrality values and then get the ranking of the vertices. You see what I mean? So it's not, if we just want the ranking, like what? Vertex 5 is ranked first, and then vertex 4, and then vertex 2, and then vertex what? 1, and then vertex 3, and then 0, 6, and 7, they all have 0. So if this is what we need at the end, the ranking of the vertices based on between a centrality, we are not interested in the actual values, just the ranking. We are going to see that there's really no need to spend all this time to compute these values. We can use another metric, which is a computationally light metric. It's called the LCC'DC. It's based on the local clustering coefficient and degree centrality. So we saw this local clustering coefficient in the first module. If you remember how to compute local clustering coefficient, we'll go through again. So we'll see another centrality metric that captures the essence of between a centrality. Okay, and if you find those values for LCC'DC and rank the vertices, that ranking is going to be almost the same as the ranking of the vertices based on between a centrality. Okay, so if you look at the numbers again here, 5 has a larger value for this metric, and then what else? The next largest value is 2, then you have 4, and then you have 1, then you have 3, and then you have 0, 6, and 7. So it's almost the same, not be always the same. Okay, so this is the ranking of the vertices based on LCC'DC. And this ranking is very much similar to the ranking based on between a centrality. The only difference is here, 2 and 4 and 4 and 2. Okay?
So how do you find LCC?
Yeah, I'm going to show you. I'm just motivating. Okay? So we are going to see how to compute such a computationally light metric that is having high correlation with the computationally heavy between a centrality. So later, after seeing how to compute LCC'DC, we'll compute this correlation based on this ranking. Okay? Alright, so let us go one by one. So how to compute the local clustering coefficient? So first of all, what is local clustering coefficient? We saw this in the first module. Do you remember?
Yep.
So given a graph, we want to compute the local clustering coefficient of every vertex in the graph. So by definition, local clustering coefficient of a vertex is what? The probability that any two neighbors of the vertex are connected. So let us pick up a vertex, say vertex 5. So how many neighbors that vertex 5 has? 5 neighbors. So 1, 3, 7, 4, and 6. So these are the 5 neighbors of vertex 5. Now, how many of those neighbors are connected? So 4, So 4 of those, 4 pairs of those neighbors are connected, isn't it? So you have 5 neighbors and you have 4 edges connecting the neighbors. So if you have 5 neighbors for vertex 5, what is the maximum number of edges you can have among those neighbors? So which means if all those neighbors are directly connected to each other, how many such edges you need to have to directly connect any 2 neighbors? Like in this case you have 5 neighbors, right? For vertex 5. So it is 5 times 5 minus 1 over 2. So you need these many edges to connect these neighbors to each other, isn't it? Okay. So always remember, if you have n vertices or n neighbors, like in this case, to connect all of them to each other, you need n times n minus 1 over 2. So why, for example, you have say 4 neighbors, you need 3 edges to connect these 2 other nodes. Then this guy, you need 2 more edges. So 3 plus 2 plus 1, right? So in general, so if you have 1 plus 2 plus up to, you have n neighbors means you need to have n minus 1 edges, then n minus 2 edges and so on. So the sum of these, this is n times n minus 1 over 2. So clear? So this is for the number of edges needed to connect n nodes.
The number of edges connected needs to connect for neighbors, right?
Yeah. So if you have 5 neighbors, you need 5 times 5 minus 1 over 2 edges to directly connect those neighbors. So let us pick up a small number. So let us say you have 4 nodes. You have 4 neighbors. So how many no edges you need to directly connect 4 neighbors? You need
4.
this 1 edge. Let us pick this neighbor. You need 1 edge to connect this neighbor, 1 edge to connect to this neighbor, and 1 more edge to connect to this neighbor. So 3 edges so far. Then for this vertex, you need 1 edge to connect to this guy, 1 edge to connect to this guy. So 2 edges. Then 1 edge to connect this one to this. So 3 plus 2 plus 1. So in 6. So in general, if you have n neighbors, it's like n minus 1 edges to connect to everyone else, right? Then n minus 2 edges to connect the other neighbor to everyone else and so on. So that is why I wrote that summation. 1 plus 2 up to n minus 1, which is what? From your math class you should know it as n times n minus 1 over 2. Okay? So that is what you need to know. If you have say 5 neighbors, it's going to be 5 times 5 minus 1 over 2. If you have 4 neighbors, it's going to be 4 times 4 minus 1 over 2, which is 6. Okay? Is that clear? So, this is the maximum number of links you can expect to have if you have 5 neighbors. And how many links actually are there in this case? 4, right? So that is this ratio or the fraction. 4 divided by is the actual number of links. This is the maximum number of links. So this is the local clustering coefficient of vertex 5. Okay. So similarly, you can compute the local clustering coefficient of every vertex in this graph.
So it's on first chapter, right? It's on first chapter, yeah.
Yeah, so now you remember.
No,
So
I
did already.
did the first, exam 1 first question also.
Okay. Yeah, so now I think I mentioned this terminology also during the first module. So to compute this without making any mistake, you can draw out like this what is called. So what I did here, or draw here, is called the ecocentric network of vertex 5. So looking at that vertex 5, so you want to compute the local clustering coefficient of vertex 5. So from this graph, just extract out that vertex 5 and its neighbors. as well as the edges connecting the neighbors. Okay? So this is the local clustering coefficient of vertex 5. So if you want, say, the local clustering coefficient of vertex 1, just extract out vertex 1 and its neighbors, 0, 2 and 5, and the edges connecting the neighbors. So this will give you more clarity, instead of looking at the whole graph and making some mistake, you can draw the egocentric network of that specific vertex, and now you can count the number of edges connecting the neighbors. So for vertex 1, the 3 neighbors are 0, 2 and 5, so how many edges are there connecting the neighbors in this case?
1.
Just this one edge. So you have 3 neighbors, so what is the denominator? The maximum number of links you can have with 3 neighbors is what? 3 times 3 minus 1 over 2, right? If you have 5 neighbors, it's 5 times 5 minus 1 over 2. If you have 3 neighbors, it is 3 times 3 minus 1 over 2. What's the numerator? 1. So that's the local clustering coefficient of vertex 1. Okay? For vertex 2, you have 4 neighbors, 0, 1, 3 and 4. So what's the denominator? What? For local clustering coefficient of vertex 2, what's the denominator? I just said you have 4 neighbors, right? So 4 times 4 minus 1 over 2. So what's the numerator? How many edges are there between the neighbors? 6? The denominator is 6, but what's the numerator? Actual number of links? 2. 2. Between 3, 4 and 0, 1. Isn't it? So only 2 edges that are actually out there, and you could have at most 6 edges like that between the neighbors. Is that clear? Okay? How to find a local clustering coefficient? Any questions?
So we can say like a 2 into number of neighbors connected by degree into degree minus 1.
Yeah. 2 times what?
2 times of number of neighbors connected.
Why you have to multiply this by the number of neighbors connected? This is the actual number of neighbors connected. That is what.
Yeah.
Yeah. So this is number of neighbors is same as degree.
Degree of the particular neighbor.
What is particular node? So 4 is the degree of vertex 2.
Okay, means no, you are just extracting all, so I got confused with them. So
I'm just picking out the neighbors, right?
Yeah. Got it.
Okay. So now look at this local clustering coefficient a little bit more in detail. So if all the neighbors of a vertex are connected to each other, right? So like this, if you're looking at a vertex and let us say it has 4 neighbors like this, if all its neighbors are connected to each other, do they have to go through this vertex for shortest path communication?
No.
If the neighbors are connected to each other, they can use those edges as a shortest path to each other. So only if a node, if the neighbors are not connected to each other, then they have to go through, like here. If 1 has to communicate with 4, since they are not connected to each other, the shortest path would be from 1 to 2 and then 2 to 4, right? So only if the neighbors are not connected to each other, you need to go through the vertex that we are looking at. So here looking at vertex 2 and its neighbors. So if those neighbors are not connected to each other, then they will need to go through vertex 2. If they are connected to each other, then they don't need to go through vertex 2. Like for example 3 and 4, they can use that edge as the shortest path between them. So if they go through vertex 2, it will not be a shortest path, right? So what is the idea you get here? If a node has a larger LCC, local clustering coefficient, isn't it? Then do you expect that node to have a lower betweenness or a higher betweenness? A node with a high local clustering coefficient. So when I say a node has high local clustering coefficient, what does it mean? What is the
high
local?
connection.
Huh?
High connection between the neighbors.
Right. So in this case, what is the local clustering coefficient of this node? We have 4 neighbors, right? So the denominator is 4 times 4 minus 1 over 2. What's the numerator? We have all those 6 links, so it's going to be 1. So on the other hand, if you have a node with the neighbors not connected to each other at all,
0.
its local clustering coefficient is going to be 0 edges between the neighbors, and then the denominator is of course the maximum, so it is 0. So if a node has a high local clustering coefficient, it's more likely to have a what? Lower betweenness centrality.
Low between centrality.
Why? Look at this. Does any neighbor of this node will go through this node for shortest path communication? No, because the neighbors are connected to each other. They will not go through this node for shortest path communication. So this is a local point of view. Now, if your neighbors don't go through you for shortest path communication, do you expect some distant node to go through you for shortest path communication? No, right? So only if your neighbors go through you for shortest path communication, there are more chances that some distant node will also go through you for shortest path communication. Does it make sense? Just visualize. So if the neighbors of this node doesn't go through this node for shortest path communication, if some distant vertex out here will not go through this node for shortest path communication, isn't it? So in essence, a local metric, like local clustering coefficient, local metric means it just looks at the node and its neighbors. Essentially captures what a global metric. A global metric means, between a centrality you find the fractions for all pairs of vertices and add them up. So it's like a global metric, looking at the whole network. So local clustering coefficient essentially captures what between a centrality captures. That's just a reverse way. A high local clustering coefficient means a low betweenness. Similarly, a low local clustering coefficient more likely will correspond to a high betweenness. So now we will try to make them directly correlated. So how to make them directly correlated? Just take the complement of local clustering coefficient. So complement of local clustering coefficient means 1 minus LCC. The local clustering coefficient values range from 0 to 1. So when you take 1 minus of that, it's still between 0 to 1, but just in the other or reverse way. Is that clear? So the local clustering coefficient, the complement of LCC prime, that's how we call it. So what is the LCC prime of this node? It's 1 minus 0, which is 1.
So what you did, I didn't understand.
The complement means 1 minus. So LCC is local clustering coefficient, so LCC prime is 1 minus LCC. So the local clustering coefficient of this node is 0. So the complement of the local clustering coefficient LCC prime is 1 minus 0, which is 1.
Why you find like?
You want to capture kind of like a direct relationship. What I mean by direct relationship, so once I define LCC prime like this, high LCC prime also means what?
Low BCC.
Low LCC, yeah, low LCC prime complement.
Okay, but that is equal to low BCC.
Yes. Similarly, high LCC prime is kind of similar to high betweenness centrality. Right? So now we want to kind of compound this. Compound this means magnify the impact of the local clustering coefficient along with the number of neighbors. So which means if a node has several neighbors like this and none of them have edges connecting themselves, you don't have any edges between their neighbors, then so compare this node with another node that has say just two neighbors like this. Okay, so a node with two neighbors like this, they are not connected to each other, and a node with say 10 neighbors like this that are not connected to each other. Which node will have a high betweenness centrality? This node with two neighbors not connected to each other, or this node with say 10 neighbors not connected to each other? Which node is more likely to have a high betweenness centrality?
Would they be equal?
Middle.
This one, right?
Oh.
Why? Because all these neighbors that are not connected to each other need to go through this node for shortest path communication, isn't it? Can you visualize this? So if this guy want to communicate with any of these neighbors, it has to go through this node.
So
Isn't it?
PWC is high.
Yeah, so each neighbor has to go through this node to communicate with the other neighbors. On the other hand, this node will go through this node, but there's only one pair like that, isn't it? Okay? So if there are several neighbors or pairs of neighbors that go through this vertex for shortest path communication, again, that means what? There's going to be several node pairs going through this, right? On the other hand, only one pair is going through this. So now you want to capture the presence of a larger number of neighbors along with what? The neighbors not being connected to each other. So that is why we take the product of LCC prime with the degree centrality. And I call this as LCC prime DC, which is basically the product of the complement of local clustering coefficient multiplied with the degree centrality. So the larger the degree of a vertex and larger the LCC prime value. So LCC prime means what? It's a measure of the fraction of the vertices that are not connected to each other, of your neighbors not connected to each other. Is that clear? So larger LCC prime means like this. You have very few edges connecting the neighbors. So most of your neighbors are not connected to each other. They have to go through you. And if there are several neighbors like that, that is like the degree centrality. So the product of these two essentially captures what? How many, what is like, how many neighbors are there and what fraction of them go through you for shortest path communication. So this is what LCC prime DC is, and we have found that to have a very strong correlation with betweenness centrality. Nodes with larger LCC prime DC are more likely to have a larger betweenness centrality and vice versa.
Sir, I got the concept, but can you please go through the terms? I'm not getting
LCC prime means complement of local clustering
that's
coefficient.
the one.
So the product of the LCC prime and degree centrality is denoted as LCC prime DC. Just a notation.
What is the DG?
DG means degree centrality, degree.
Yeah.
So multiply degree with LCC prime.
Okay.
And that is what I indicate as LCC prime DC. Again, DC means degree centrality. Okay? So these two metrics are equivalent, means strongly correlated to each other. Okay? They are not equal, equivalent. So nodes with larger LCC prime DC are more likely to have a larger betweenness centrality and vice versa. So if you look at this numbers here, that's what it indicates for this example graph. So nodes with larger LCC prime DC, like 3, have a larger betweenness centrality. So phi. So if they have a smaller LCC prime DC, they also have a lower betweener centrality. Okay? Is that clear? So let us complete this example. So to find the LCC prime DC. So you all know how to get the LCC values, right? Look at the number of edges.
Neighbors and connected and degrees.
The actual number of links divided by the maximum number of links possible. Okay? So that's the ratio. Then compute 1 minus LCC. So 1 minus 1 is 0, 1 minus 0.33, 0.67 and so on. Then multiply the LCC prime with the degree. So you already got the degree of the vertices. So 2 times 0 is 0. Then 3 times 0.67 is 2.0. Then 4 times 0.67 is 2.69 and so on. So that's LCC prime DC. So these numbers can be used to rank the vertices based on betweener centrality. So I remember the ranking I wrote before. So such a ranking is going to be very similar to the ranking based on betweener centrality. Okay? So I'm going to show how to compute the correlation of these two rankings. Okay, so there's a name called Spearman's rank-based correlation.
Sir, I have one question.
Yes.
Between centrality, how to find the between centrality? BWC, now above they have values, right?
Right. So the method we saw before is to compute the fractions, and you have to compute such fractions for all paths and then add. But again, as I said, it's time consuming. So go back to the executable files I gave you. I gave you 6 files. So one of them is to compute betweener centrality. Okay. So as usual, prepare the adjacency list for the graph, load it to the program. It's going to print out the betweener centrality of all the vertices.
Okay.
So try it out, and if you cannot run it, let me know. It's same as like computing eigenvector centrality. Okay. So that is how you get the betweener centrality of all the vertices. Okay, so now for this graph, we got the betweener centrality and the LCC prime DC values. So I want to now compute the 3 correlation coefficients. So starting from the rank-based correlation coefficient. So what I mean by the rank-based correlation coefficient, you got the ranking of the vertices, right, based on these 2 metrics. So how similar are these 2 ranking? Okay, so these are the 8 vertices. These are the betweener centrality values. Now start with what is called the tentative ranking of the vertices. So what is the tentative ranking of the vertices? So start the rank. The nodes with the larger rank means the larger betweener. So start with the smaller value. So 0 is the smallest value. There are 3 vertices with the smallest value of 0. So you have a tie here. So the tentative rank, you break the tie by just going with the vertex ID. So the vertex ID is 0, so that vertex gets the lowest rank of 1. The other 2 vertices 6 and 7 that also have a betweeners of 0 get the rank 2 and 3. So that's how you get the tentative rank. If you have a tie, just break the tie based on the vertex ID. Okay. The next smallest value is 0.33, so that is rank 4. The next smallest value is 2.33, so that is rank 5. The next smallest value is 4, that is rank 6. The next smallest value is 4.33, rank 7. Then you have 5, which is 8. So the largest betweenness means you have a larger rank number. Okay? So the tentative rank numbers are unique. So if there's a tie, break the tie based on the vertex ID. Okay? So that's the tentative rank. So now we have to come up with what's called the final rank based on that metric betweener centrality. So the final rank is same as the tentative rank if there's no tie in the centrality values. But in the case of 0 for centrality value, you have 3 vertices that have the same centrality value. So you break the tie in the case of tentative rank by assigning 1, 2 and 3 the order of the vertex IDs. For the final ranking for these 3 vertices is going to be the average of those tentative rankings. So what is the average of tentative ranking? 1 plus 2 plus 3 is 6. Divided by the number of vertices that have the type, 3 vertices. So 6 divided by 3 is 2. So that is the final rank for all those 3 vertices, which is 2, right? So the average of the tentative ranking, 1 plus 2 plus 3 is 6 divided by 3 is 2. So that is the final rank for those 3 vertices. Now for the other vertices, there's no type. So the final rank is same as tentative rank. So the final rank of 4 is same as tentative rank, 5, 5, 6, 6, 7, 7, 8, 8. So that is how you find the final ranking of the vertices based on the particular metric. Okay? So do the same thing with respect to LCC prime DC values and obtain a final ranking of the vertices. So for LCC prime DC, again you have 0, 0 and 0 as the value for these 3 vertices. So the tentative rank is 1, 2 and 3. And then you have 1, so that is rank 4. Then you have 2, that is rank 5. Then 2.5, that is rank 6. Then 2.67, that is rank 7. And 3, rank 8. So that is the tentative rank of the vertices based on LCC prime DC. So again compute the final ranking based on this tentative ranking. So there's again was a tie between what these 3 vertices. So just take the average of those tentative rank 1, 2 and 3, 6, 1 plus 2 plus 3, 6 divided by how many vertices? 3 vertices. So 6 divided by 3, 2. So that's the final rank. Then the other vertices did not have any type. So the final rank is same as tentative rank. So this is the final ranking of the vertices based on LCC prime DC. This is the final ranking of vertices based on betweenness centrality. So we want to see how close are these rank numbers, the final rank numbers for these 2 metrics. Okay? If they are all the same, then the correlation coefficient is going to be 1. If they are very different from each other, it's going to be a lower value. Okay? So it also ranges from -1 to 1, like the Pearson's correlation coefficient we saw before for sortative index. Okay? So this is the formula. So let us see how to fit in this formula. So once you get the final rank of the vertices based on these 2 metrics, find the difference between the ranking. So 2 as a final rank between a centrality, again 2 based on LCC prime DC. So 2 minus 2 is 0. The difference in the ranking is 0. Then 5 minus 5, it is 0. So you have 6 minus 7, -1. So the difference in the rank numbers for the vertices. Then 4 minus 4, it is 0. Then 7 minus 6, it is 1, and so on. So once you find the raw difference in the rank numbers, just square them. Okay. So -1 square will be 1. Again, 1 square is 1. So once you square them, that's the difference. Square of the difference in the ranking. Sum all those squares. So sum all these values. In this case, it's just 1 plus 1, 2. Then plug it in this formula. So 6 times the sum of those squares of the differences in the ranking divided by n is the number of vertices. So in this case, 8 vertices. So n times n square minus 1. The whole thing, do a 1 minus of that. Okay? So 1 minus 6 times 2, in this case, divided by 8 times 8 square minus 1. So it comes to up to a very large value, 0.98. So that is the correlation. So 0.98 is very close to 1. So the ranking of the vertices based on betweenness centrality and based on LCC prime DC is very similar to each other. Okay? So that is how you compute the Spearman's rank-based correlation coefficient. So this is to what? So with this approach, we can say that I can rank the vertices in the graph. If I want to rank the vertices based on betweenness centrality, I don't need to really compute betweenness centrality. I can just compute the LCC prime DC values of the vertices and rank the vertices, and that is going to be a very similar ranking based on betweenness centrality also. Is that clear? As you can see the numbers for the final rank. So next time what we'll see is it's not just the rank based correlation. We can do also what's called the Pearson's correlation, which means trying to predict the values of betweenness based on the LCC prime DC values, the actual values of betweenness based on LCC prime DC values. And you can also do what is called concordance based correlation. So what it means is if they be doing something like this, picking any two vertices, say Vi and Vj, if the betweenness of Vi is greater than the betweenness of Vj, is the LCC prime of Vi also greater than LCC prime of Vj. So instead of ranking the vertices globally, ranking all the vertices, I just pick two vertices, Vi and Vj, and I want to say whether Vi has a larger betweenness or Vj has a larger betweenness. So we can say Vi has a larger betweenness than Vj. Instead of directly computing the betweenness of Vi and Vj, we can compute the LCC prime DC of Vi and Vj. And if the LCC prime DC of Vi is greater than LCC prime DC of Vj, how likely is the betweenness of Vi greater than the betweenness of Vj? Is it clear what I mean to say? Instead of directly computing the betweenness and wasting time, what if we just compute the LCC prime DC of the two vertices? And based on that, can we say something about the betweenness of the two vertices? Right? So how close can we say that? Again, in a scale of say -1 to 1. If the correlation is 1, it means just based on LCC prime DC of the two vertices, we can compare the betweenness of the two vertices. So it's like a pairwise correlation. Okay? So we'll compute the correlation coefficient for these two measures to predict the betweenness centrality values as well as to compute pairwise, okay, the betweenness centrality values of the vertices. Okay, so we'll continue this next time.